This is episode 2 of this Mathcounts series, Arithmetic Part 2. Today we'll be looking at some tricks for some faster calculations. First, let's look at some large sums. Well, not quite yet. Let's first look at just 1 plus 2 plus 3 plus 4, a small sum, and this is just equal to 10. But what if we encounter something like this? Or something like this? Well, these are definitely not easy to calculate by hand. At least I don't want to calculate these. So what do? Well, let's first look at sums that look like this first one here. That first sum had a format that looked like this. It's 1 plus 2 plus so on and so forth until some value of n. And this sum is said to be equal to n times n plus 1 divided by 2. Well, let's prove it. So taking the sum I showed you previously, 1 plus 2 plus 3, so on and so forth until 100, let's try adding opposite terms. So 1 to 100, 2 to 99, 3 to 98, and so on and so forth. So adding these terms together, we have these pairs. And these pairs, if you look at them, each of them are equal to 101. So we have some sum of 101s. But how many 101s are there? Well, we had 100 values originally, and we paired them off. So 100 divided by 2 is 50. So we have 50 101s. Pretty easy. Now we can just calculate what our sum is equal to. But we wanted to prove our original rule. So let's try reformatting this expression to look like our rule. We have 101, which is 100 plus 1, which is our n plus 1. And we have 50, but we don't have n, and we don't have divided by 2. But looking at 50, we can rewrite it as 100 divided by 2. So this expression is actually equal to 100 times 100 plus 1, all divided by 2, which has the same format as our original rule. And our sum is just equal to 5050. So this rule works for any sums of consecutive positive integers starting from 1 to n, where n is any positive integer. Now let's look at the second sum that I showed you previously. The sum is 2 plus 4 plus 6, so on and so forth until 36. And it looks like it's a sum of even integers, even consecutive integers from 2 to 36. Let's take the same approach. Let's add 2 to 36, 4 to 34, 6 to 32, so on and so forth, and we get a sum of 38s. Well, how many 38s are there? There are 18 even positive consecutive integers from 2 to 36, and 18 divided by 2 is 9. We're dividing by 2 since we paired these values. And so there's 9 38s. 9 times 38 is 342, and that is the answer to our sum. So this approach works for any sum that has some sequence of values. Now let's look at this sum that I did not show you previously. This sum is somewhat different from the previous two sums that we looked at. There's still a sequence among this sum, but this sum has an odd amount of values. So let's try taking the same approach again. We have 2 plus 14, 4 plus 12, 6 plus 10, but we have 8 left over. Well, this 8 is the median of our sum. It's the median value among the values of our sum. And so each of the pairs here is 16. So our sum is just going to be 16 times 3 plus 8, 48 plus 8, which is equal to 56. So the general approach to a sum with an odd amount of values is to find the value of a pair and multiply it by the amount of values minus 1 divided by 2. So here we had 7 values. 7 minus 1 is 6. 6 divided by 2 is 3, and so we had 3 pairs, and we multiplied by 3. Our pair value was 16. And then after finding the value of the sum of the pairs, you always have to make sure to add the median. Now moving on from sums, well, not quite. We'll look at this sum, but it's a sum of products. We have 1 times 4 plus 2 times 9 plus 3 times 14 plus 4 times 19 plus 5 times 24. So immediately looking at this, you can see the 1, 2, 3, 4, and 5. But how is this going to help us? It's not really going to help us right now. But if we look at the other values, we can see that each of these values is 1 less than a multiple of 5. So let's rewrite this as 1 times 5 minus 1, which is 4, plus 2 times 10 minus 1, which is 9, plus 3 times 15 minus 1, which is 14, plus 4 times 20 minus 1, which is 19, plus 5 times 25 minus 1, which is 24. So now we can just use the distributive property to get this, where we distributed 1 to 5 minus 1 to get 5 minus 1. We distributed 2 to 10 minus 1 to get 20 minus 2, so on and so forth, 45 minus 3, plus 80 minus 4, plus 125 minus 5. Now let's separate the positive values from the negative values and get 5 plus 20 plus 45 plus 80 plus 125 minus 1 minus 2 minus 3 minus 4 minus 5. Now let's just add all the add all the positive values together and all of the negative values together and get 275 minus 15, which is just 260. So this approach can be taken to any sum of products where there's some pattern among the values in the products. So to sum it up, all of these, or most of these arithmetic problems in Mathcounts are some manipulation of the commutative, associative, and distributive property. You've probably learned these. Just remember these. And also the distributive property can be reversed. This is known as factoring, when instead you take out a factor instead of multiply by a factor. I will attach a practice in the description box below. I will also provide my email where you can ask me math-related topics, ask me math-related questions, suggest me math-related topics to do in the future, or just chat with me about math. Thank you for watching this video. I hope you enjoyed it and learned something new. Have a nice day.